Okay. Oh, thanks. So, all of you, hello, welcome. The last 1 hour, more than an hour, about 2 hours, close to 2 hours, we have been discussing about the planning, scheduling, and logistics of this conference that we are having in May. And I think we have come up with many resolutions. And then, so right now, Christopher is going to modify the website to include everything. Right now, we have, I think, the 30th, which is the main conference day. I think we have everything uh, right now decided, and so he's going to modify that website for the 30th especially. So we'll everybody will know what each speaker is speaking. All of them are invited keynote guest speaker presentations, hybrid, which means that we have about in person, four of us, I think, five of us almost in person, and then Emmanuel will be online uh, virtually, so he'll be presenting, uh, you know, through the virtual line. That Christian is going to work on the all the IT aspects along with his son and his uh, girlfriend. So they'll be setting up everything, and we hope to have everything ready on 29th so that we are ready to go on the 30th. So 29th we'll have the meeting, and then right now with Laszlo, we are arranging to have a visitation to atomic key nuclear facility that's we're working on, and he has given me the email address of the head of that. So I'm going to send an email so that they will give us permission or pass whatever is necessary to visit them. And there are two locations again. That's another thing we have to figure out where they're going to let us see. Uh, so depending on that, that will be most likely the 31st, which is the Saturday. So 29th, we have the I arrive and everybody would have arrived by then. So we have the luncheon and the meeting uh, and other things that's going on that day, especially preparation for the conference. And the 30th is the actual conference, the whole day. And the evening, probably we may have dinner banquet, but then we'll get ready to go to our, our visiting sightseeing and things like that. So 31st will be then the first will be essentially it's up to each person mostly. They can either join the group or they can have their own city and sightseeing and everything. So it's a flexible day where so essentially the main where we all of us meet on conference day, which is the 30th and the 31st uh, part of it. So essentially that's it. So it's a one-day conference, and then we hope to have half yearly annually where we can have more number of days, more number of sessions with the session chairman and more presentations, things like that. So whatever extra is here will be carried over to that. What I'm saying is that there may be other people who want to present or join that. So, but we will postpone it to the next one. Now, the important thing is deadlines. So, those who are the speakers, they have to send their abstracts and their bios to Christopher by March 15th. We are extended to March 15th, so everybody can have that. But by that time, you should be able to prepare your presentation, and we want to have a video, MP4 or any other type of video, whatever video is suitable, and we have to decide that by March 31st. So what we want to do, the way we want to do the conference is the following. And talking with Christian also, we don't know exactly how things are because it's a foreign country for all of us, but things can go wrong sometimes. So we cannot expect everything to be perfect. But if you have the video, we'll have the video actually playing that, and you can play the video like 5 minutes and then explain them. So that way, you are not, even if you are not at your best level, health wise, other things, you can still present it. So Then you can present, you can explain them each video and then go from there. So then you can play 5 minutes, explain that, so that we increase the amount of no the understanding people have. I believe so far, my experience is that about 10% people understand, about 10%. If I look at myself of what is presented, to be honest, could be sometime less, could be sometime more.
Are we not expecting the presentations to take the form of like slides rather than videos?
It's up to the. Oh, that's a good point. I think we should decide that. I think it should be a standard. I would think that.
There's two options, right? If you're there in person, then we would expect you to give the presentation in person, obviously. But if you're giving the presentation remotely, like online, then we'd expect you to give it in person online. But if there's for some reason you cannot do that and you have a pre-recorded video and you're remotely, presenting, then that's fine. It could be okay to show the video, but it would mean that you'd have to be present afterwards when the video's over for questions, so you can answer questions. And that's the only stipulation.
Different.
Okay. But in general, it's to be there in person. But if you can't do that, fine. Remotely online present, and then thirdly would be like a video, pre-recorded video. But yeah, so those would be the order of like preference for presentations, I think. And it'll be a slideshow. I'll probably make a template for the event, but it's not. I don't think I'm going to hold anyone. You can use whatever slideshow template you want. The template is just there if you feel like you need to use it.
Okay. But I would think that it's good to not only the abstract and bios, but your transcript of your talk, video presentation by March 31st, because that will help if we are to, if there is some problem in the issue with IT and things like that, we can actually, even for in person, we can have the video play and then the presenter can explain that. So that will make it easier.
No, I don't think that's necessary. I think they'll just get up, they will deliver their presentation, and then they'll take questions, and that will be it, because their time will be limited anyway. We won't have enough time to set up videos, and people might not have the capabilities to make videos. So I don't think we should be. There's no need for that as a requirement, I don't think, unless I'm misunderstanding what you're saying. But as I understand it, I don't think that's necessary.
Okay. So if possible, I'm saying if possible, those it's possible for people, we will encourage people to send their transcript. So
no need for transcript at all. Just get up, deliver your speech. Deliver because there's no reason to suspect that everyone will be operating off a transcript. I know that one person is, but for the most part, many people might get up and just deliver it directly without any script, and that's what I would expect people to do. In general, that's what people do. So, but if there's a language barrier, some people might like to.
That's right.
And
that's what I'm saying.
They have some months to prepare a script, and then they can even have it in phonetics, or they can have definitions of words if they need to. So then they'll be able to read it in English, preferably, and then they could take questions in their own language. If they have a translator, that would be the best.
So Astro may have that.
Otherwise, we expect the conference to be in English just to keep it like homogenous, so it's not skipping between lots of different languages that not everyone might understand. But yeah, so that's it. It would be nice if people are thinking of if there's a language issue and people want to read from a script, from a transcript, then that's fine. But they can give us the transcript and we can translate it into their native language, and then may possibly have that as subtitles. Or we could choose, say, right, English is maybe the main language of the conference, and then German, maybe, because most people seem to be German. So German
Hungarian,
is the
Hungarian
second
also.
language, and then we could have subtitles on all the videos because the entire conference is going to be live streamed, and the subtitles for the conference will be in German. I think that's fair, isn't it? And then, but we should be aware that those subtitles are going to be generated automatically by YouTube, so it'll take some time before they're processed and available to the public. So if there's some way that we could have live translation of the transcript, Rajan, I know that you have a tool on your, when you present slideshows,
closed caption, captioning.
It dictates what you're saying, but you see, it will dictate it in the language you're speaking in, it won't translate it into German. So that's a problem that I don't have the technical ability to solve that. I mean, we could look it up, but
we'll say Christian. We can ask Christian.
Oh yeah, great. Yeah, that would be it. I think Christian will be able to deal with that. Okay, so what's the? Is that seems to be pretty much all the main topics.
Pretty much, yeah.
We need to still need to announce where the conference is going to be held.
Yes.
Yes. So that will come in time.
Yeah, we ought to get information from Christian pretty soon. I think we can send an email to Christian to let us know what he has come up with, and then whether the venue is fixed, or whether the hotel, because the idea right now is to have the conference in the same hotel as where we stay, so that there's no issue of transportation.
Well, either way, like, provided if the hotel is quite central, we know that all those universities are very central as well. But by the sounds of it, if we can get a good deal, it will probably be in the hotel. But if it turns out to be cheaper in the university or something, then that would be cool to be in the university as well. So we'll see how that goes. Okay, so what are we discussing then today? We've got a couple of different topics, I think. But
so I don't know, you have something, Christopher, but Laszlo has something about ball lightning.
Yes, so Laszlo, you produced a paper on ball lightning.
I don't have anything yet. I don't know because majority of my articles is not related to such a physics what you are supporting, and in this case I don't know what I can do, because
I'm going to ask you some questions about it. Just one question, really. So in the paper, you're talking about an experiment that you did while you were in China. I was wondering.
Okay, it's okay. And now about the article of the lightning in relation to gravitation, and now I am writing the article about the ball lightning.
Oh, okay. So
and these three subjects can be adjudicated in one presentation. It's correct?
Well, that's up to you. Normally, you would try and keep the presentation on one subject, but if it's like you can decide, like, how am I going to make these three different subjects, let's say,
what I can do on another form, because total this theory comes from the planet region. Do you know when I formulated this phenomenon?
Yeah, so it depends on yourself. Yeah. So, for instance, if let's say you're talking about gravity and lightning, and then you talk about ball lightning. So those are two related topics because they both deal with like atmospheric,
It's not related to the atmosphere. It's related to the space phase of the Earth.
No, but I mean,
it's totally related to the gravitational. It's total novel idea.
Okay, but lightning happens in the atmosphere, doesn't it? Lightning happens.
It is not atmosphere is related to the condition of the Earth space phase, phase, its relation to it. Do you understand?
Yeah, but it's lightning.
Because there is a lack of the and is filled up to the atmosphere.
Okay, so
atmosphere it's another thing.
When you're talking about lightning, are you talking about lightning that happens in
lightning? It's related to the clouds. Okay, it's related to the clouds, and when lightning happening,
yes,
then it affect the Earth's space phase. I will.
That's very technical, though. I think that's part of your maybe the entity you're talking about, or the a priori entity or something, or maybe that's a separate thing. But the point I'm making is, if you want to just collect a few different ideas under one topic, then you need to name it like, I don't know, like
I will make a very a list about it, and I will send to you, to your Christian, and to Ayer, and you decide it's good or not. Okay.
So yeah, you'll send it. So yeah, do send something on. I mean, you could either
because me it's very easy to speak about the plate tectonics problems, to speak about the planet erosion. It's very easy subject, but in case of physics, it's more hard for me. But in this case, if I use this approach, yeah, I don't have problem.
It's all like the earthquakes and well, that would be geophysics. So it's
earthquakes is total different thing. Earthquakes, my earthquakes concept is not related to the mainstream earthquakes concept.
That's
it's
fine.
Total. It's total different. Okay, and I didn't made article because I want nobody helped me to have a chance to test them, because I think that the earthquake forecasting it's resolved, well, and nobody interested in it.
That's a good point, actually. Whatever you're going to present should be either be a paper already that hasn't been published before, or
I will not make about the earthquakes. I don't want. If you make your project, I will help you.
Then it would, if you're not going to make a paper on it, I wouldn't present on that topic, because there's going to be proceedings of the conference, and those are going to be papers. So as long as your paper hasn't been published anywhere else, just decide, I'm going to write a paper on this, or I have a paper that I've already written that hasn't been published on some subject, and then that will be the topic of your presentation. Remember, you only have 20 minutes anyway, so that's something to consider.
Yes, and something I wanted to ask you. No, I don't know now.
Okay, you forgot. We'll come back to you. So I was going to ask you a question. So you have this article that you wrote about gravitation and lightning and the effects that...
this is ready, approximately ready, but I have to get more information about the theories. I have spoken, I have told to Ayer before that I am using artificial intelligence in this case and verifying in literature, but that is a very long. It is very long time for it, no, because it has a high literature, and I told before that that majority of the theories can be unified in a single theory of ball lightning. Seems that exists, that is possibility, and I don't know. I have to study, and I can get the information about the Tesla concept of the ball lightning, because I think that Tesla had good points in this subject. We know well that his concept of electricity, it has a great
Yeah,
Tesla.
that's great.
Tesla, and I think and then I think that Tesla also have a concept of electromagnetic gravity theory. He has.
Right. Okay,
he had this concept.
Right. So what I was asking about was the gravitation lightning thing, not the ball lightning, because I noticed in that article you mentioned you traveled to China and then you were going to do an experiment over there. So
That is a
Can you wait until I ask the question before answering it?
I have made videos.
The question. So I was just wondering if you'd be able to give us some details on that experiment or the details of that experiment.
It's a very simple measurement with the balance in lot of places, and was repeated these measurements.
Okay.
I repeat it, but it will be good to we will meet in Budapest, and I have videos about it, and I will show. Okay.
So are they on your YouTube channel?
I didn't put yet. I didn't put it because I like to go a bit time, and I would like another thing, but I don't know the software, because before 10 years, when I have written my first article about the gravity. The gravity can be demonstrated with facts. I made a simple algorithm with the software, but actually the software doesn't work, and I don't know the name of the software. But if I will know, perhaps you have, and we can again repeat this algorithm.
Okay,
because this algorithm helped me to predict tides of the Mercury, tides of the Venus. I didn't make tides forecast for Mars. Okay, and that is very, very important. It's a very, very, very good software, but I don't know. Perhaps you have, perhaps higher it has too, and I have observed that this software also is used by Ukrainian earthquake forecaster Yagodin, no, not Yagodin, Vyacheslav Nagorny. You don't know him.
No,
you don't know him, but he made a very good article of forecasting. He tried to forecast earthquakes in Japan before 5-6 months of the event, and she get a very good result. He forecasting with 4 days was wrong, but at his forecast, earthquake forecast, was a problem. He doesn't use only one thing, and in this case also it needs to use dualistic. You have to make dualistic forecast, not a singular forecast, only one side, because in this case you will have a good forecast. But that is for the earthquake forecasting for short-term forecast, not for medial short-term forecast, and not the short-term forecast. Because in the case of the earthquakes forecasting, we have three type of forecast: long-term forecast, medium-term forecast, and short-term forecast. In general, the long-term forecast, and short-term forecast is medium-term forecast is only approximative. The important is the short-term earthquake forecast, because the time of the earthquakes forecasting is very, very hard. And in this case, exists a Jewish researcher. He also went to his country from Ukraine, and he made short-term forecast, very good short-term forecast. I didn't use his concept. He separately made. I didn't have information about his forecasting method, but I get the same result. I don't know. I do know what he do. Do you understand? And but in his case, he doesn't use totally deterministic forecast. In case of short-term forecast, we have to use deterministic forecast, not statistical forecast, because not to look to harbingers. You have to have installed tools for observing some phenomena. Examples: seismic stations or radios. What you did, you have presented here is in this video conference such a tools, which is very good, and that is it can be developed. These tools, what you did. Do you know what tool I am speaking now? You presented with the sound. When exist seismic signals and you have radio signals.
Oh yeah. There's a couple of different sources. I don't know any that join the two together. I think you have to go and get the seismographs from one place, maybe USGS or something, and then the electromagnetic spectrograms.
Don't need only you can receive these signals. We can make such tools which price is not so big, like you say now, because we need only seismograph. It's very important, seismograph, and for other things we need example gravitometers and some tools to get electromagnetic signals.
Gravitometers, like, would they be used to get electromagnetic signals?
Yes, three tools is very important. Gravitometers, seismic signal registrator, and electromagnetic signel. Radio signal.
You want vibration. You want a very sensitive device to pick up the Earth's signals. You'd probably be better off to just get them. They're available online. You can get all three of those things. Not sure about the gravitometric signals. I don't know. You probably might have to sort.
And of course, here is needs some geology. My profession is very, very important. You have to know very well the terrain where the earthquake happening.
Yes.
And the problem is that because of economic situation and political situation, the geology is somewhat is the current theoretical geology is somewhat is not so good for the actual geologist to have a good imagination about the real Earth surface. Example, when I was a student, same the geology had two subjects doesn't was in my study, the geomorphology and the volcanics. These two kind of part of geology is very important to have a good geological concept, and that is not was in our teachings. We don't need to make exam from these two subjects, geomorphology and volcanology. Do you understand? That is very, very important. Also in the case of the earthquake forecasting, in case of in all thing, in the exploration, in all.
Yeah, I think there can be a difference between the volcanism and the earthquakes. You know, you can have earthquakes that are.
No, I think that the majority of earthquakes is connected to volcanism.
No, not all of them are. There's a
the plate tectonics, actual plate tectonics is totally is an erroneous concept, because you are a physician, and if you look on the process of the subduction, it cannot be happen such a physical phenomenon, a physical process that light plate to subduct go in the denser matter. Do you understand? I made example this subject can demonstrate example
this is lighter than the mantle or the
I don't know if I don't know if the current concept about the mantle, crust, and the core is totally correct, because we don't have a chance to verify who invented this concept. I think that before 18 years the information was more correct, and that is why we can accept, in my opinion, that the Earth is made of from core and for rocky shell. And that other thing it's not so important. And this kind I made the new article about the ball lightning. I used this image of Earth because no more I will speak about the a priori entity. I will speak about the Earth in case of the ball lightning. Okay. Do you understand? Because in case of ball lightning, we have the Earth. The Earth has its inner the core, and is a transitional zone, the rocky shell, and outside it has the space phase, and enough, nothing else, and it is another transitional zone that is an aerial zone. It's very simple.
Doesn't sound simple. But what you can do, Laszlo, is you could try to put those thoughts together in a more kind of formal way, like an introduction, introduce the ideas, and then explain them, like maybe using like a PowerPoint presentation or something. just so we can get a better understanding, because you'd have like you need to kind of start at the beginning and like explain some of the concepts. But sounds interesting. Like, for instance, I don't know why the core of the Earth would be important to ball lightning. That's a bit of a new one on me. But yeah, I'd also like to hear more about the a priori entity. I don't really know too much about that, but it sounds like it was a placeholder for something else, that so it can now be dropped. So that's interesting, but maybe it's not as relevant as it was. And then, of course, the planetary erosion concept, that's another one that you have. So you might make a short presentation on that at some point and maybe deliver.
But of course, I have the philosophy. I have the philosophy book. There is a there is a concept is a natural ideology, metaphysical concept.
Right.
But this concept had now with actual. I wrote it before 30 years.
Okay, so what is
and only one thing is not good in this concept. What I told before about the Vyacheslav Nagorny earthquake forecasting was not dualistic.
Okay.
That is the problem of the philosophical system, because only approaching the things from ideology, ideal, not ideal. But the ideal is the essence when everything going to the equilibrium. This ideal is somewhat close to the Platonic ideology. At the more realistic, if we take the contemporary, not contemporary, the ancient Chinese Tao concept. They have say, I didn't read this concept from the Chinese, because we lived in a communistic era, and we only have Marx philosophy.
Right.
Nothing else.
Wow.
Nothing else.
That's mental.
No, but when I get this idea totally chaotic, then I wrote down, and I have two very important subjects in this book. One is the explanation of the light forming, how the Earth life operated. The total novel idea, how the Earth life was created on the Earth. And another thing is the human becoming, how we became thinking entities of the Earth.
Okay.
And with this concept of the ideal, it can be easy explain it. Total. It's very simple. Again, excuse me, I am saying very simple, but very can be explained.
Okay,
because the earth condition every time is changing. Every time is changing, and that's changing is created this equilibrium in the lives, and they have to change. And they accommodation, they making accommodation to this situation, this two new situation.
Okay.
And the example from my life, I have hard situation of living, but I didn't do nothing for to make them better, because to provoke me to thought, to have ideas, and this works. If you living in very good condition,
Yeah.
you don't have good ideas.
There's no striving.
Example, because your stomach is empty, you every time you are trying to think about how to, where do you go, where from where you can get food, but that is not a problem. But in case when you put a question, how can we resolve this situation, this situation, you can get easier responses.
Well, that's right, isn't it? That we have that phrase in English: necessity is the mother of invention.
Oh yeah.
So I think that might be similar to what you're talking about. So if you were to apply that to biology, you're saying a need arises, and then the biological system generates some new thing or adaptation to take care of that need, and so that could result in a new kind of life form or thought form. I suppose that sounds quite similar to Darwin's theory of evolution, does it? Are you on board with Darwin's theory, or would you disagree with evolutionary theory, Laszlo?
Yes.
Yeah, you're not sure.
I don't know.
During the communist era, if you only had Marx, did you also have like religious philosophy, or was that allowed? Or
I am living religious life, because my mother was a Romano Catholic.
Oh, very good. Yes.
And that is a very very important thing in my life, and that this lead to make such a philosophical concept that it can be used in case of religion, and it can be used in case of science. Is something pantheistic view about the God, because tomorrow I will go in church, but I don't have such a concept what there is a priest there. Do you understand?
Oh, I think I understand. So you're saying,
and in case of I don't know, but example, in original article of the ball lightning, I used a gospel from Matthew,
right?
And this gospel is totally containing the some
concepts
is related to the natural processes. I will send you this gospel. It's very very interesting. The good part of the religion Bible is the Gospels of Matthew. I like all his gospel.
What part of the story is it? Is it like the prodigal son, or is it a fate? What do you call those things where Jesus taught in parables? Is it one of the parables, or is it an event from the?
I don't know. I don't know, because I am somewhat. I am thinking that about what we know about the Jesus is similar what we know about the current science, mainstream science. They somewhat was changed. We don't know the real situation.
Yeah, I don't know. I think
Only one thing we know that,
we have Bibles from like
and
in these
and
early. We have Bibles going back a
and
long time,
and I want to go back to
no change.
exactly. But one thing I want to say, in case of a book of the ideal, I used not only Christian religion, I used Indian concept. Same, I used Zarathustra and Arabian religion, because one problems was I didn't have information about Baha'ism. The book and my concept about the religion concept is very close to the Baha'ism. Did you hear about the Baha'ism?
Is that Jewish? Some Jewish religion?
It's not. It's an Iranian religion, but he didn't has a lot of supporter.
I don't know.
When I wrote this book, when I wrote this book, didn't have information about the Baha'ism. Nothing. Is not.
I think the Baha'i faith. It says here Persian, but I believe it's something to do. It might be a Jewish religious sect or something like that. That's what I've.
It's totally. They has an imagination. Pantheistic, same pantheistic religion.
Yeah, I looked into it a bit. It sounded pretty interesting, but then recently I heard it was somehow connected to like Judaism, as in it's like basically Judaism before it under some other. I don't know. I'd have to look into it again, but yeah, I'm not sure. It's you know, I've heard bad things about it, so but I haven't looked into it too much. But you were looking into, was it Zoroastrianism? Was that the other one?
Yeah. So when I was in India, I attended one place in Delhi. I visited my relatives. So I went to a Baha'i place, and it's connected to Persian, but it's not the same. Persian.
Well, yeah, Persian is just a nationality, isn't it? Like for the Iranians,
but it's an offshoot of that. So it's in that region.
Maybe I have it confused with some other religion then.
Yeah,
pretty sure it's Jewish though. Jewish Academy, Baha'i Faith Jewish Academy.
It's Iranian, Parsi, those regions.
That's a good question. Jewish virtual library, like there's a lot connected here. I'm just looking at Baha'i Faith Jewish and I mean. Yeah. Okay. So there's Jewish conversion to Baha'i faith. Explaining. So there's a lot of conversions for some reason. Israeli support of Shogi and the Baha'i community. So it's supported by Israel. That would suggest that it's likely to be somehow Jewish. But who knows? So it says here that it was founded in Iran in 1863 by Mirza Hussein Ali Nouri. Known as Bahu'allah or Baha'allah, Splendor of God. So this is from the Jewish Virtual Library. So maybe they're just, but so thank you. And so this person was imprisoned or exiled, and he wrote Kitab al-Aqdas, the Most Holy Book. After his death,
I don't know a lot. I don't know a lot too. But only in few articles I read about them.
Yeah. No, I never really looked into them too much, but yeah. So I don't know why it's in the. I'll just get off this website. It's too annoying. Too many flashing adverts. So that's it. Anyway, it seems to have the backing of the Israeli state for whatever reason. So. I would assume it's not a Muslim faith, if that's the case, because they wouldn't generally back. Like it would be strange for the Israelis to be backing an Islamic faith in Iran, you know. I don't think that's
Yes.
really high on their
That
agenda.
doesn't
So.
that like that won't mesh properly.
No, I don't think so. I think there'd be some questions about that to be had by the Israeli people, like if they find out their government was sponsoring that kind of thing, which is what's kind of going on in the US there at the moment, isn't it? They found, you know, so the US is like one policy when it comes to Hamas, I guess, and Palestine, and then they also seem to be like giving them money, but I don't know really. So we won't get into a political point of view, but so going, yeah, I don't know. Well, I did have a presentation that I'm working on, but it's quite a difficult topic, and I would have made it about a month and a half ago. I haven't really looked into it much since then, so I'll just show it to you. But I don't know how prepared I am to speak on this. So perhaps I could just, I think I need to share entire screen. Okay, so this is it. I'll hide that. Oh, can you see that?
Yeah, galactic distance measurements.
Great. So I renamed it from the Anamorphic universe model to Anamorphic perspective Cosmology. And so it's now, the acronym is now APC instead of AUM, because I think APC is a bit more, it kind of hits a bit harder, you know, whereas when people say the word in a sentence, it sounds like they're saying or you know, like they don't know what, you know, that kind of thing that people do when they're trying to think of the next word, they go so it can kind of get lost in people's language. It doesn't sound, it's harder to hang your consciousness on, you know, your attention, I mean. So APC is more it's just catchier, literally. So we'll just look at previous work, which I've subtitled A Litany of Errors. It might be a bit extreme, but obviously the first one is the work that myself and Rajan collaborated on, which was the support vector machine analysis. So the idea was that we transformed all the galaxies in the SDSS data set into, we transformed it using a stereographic projection method so that all of the galaxies fit inside the first Great Wall of Galaxies as they appear in the night sky, if you think of it that way. And that required a transformation of about 70 times. So anyway, we need that kind of coefficient in the equations. But so then if we take this as one class, the transform set, and the untransformed set as another class, then we were able to use support vector machines to find the decision boundary, which is the red line here. And so support vector machines are based on the radial, that's very sensitive, radial basis function, which I think you can also use the polynomial kernel, which is just described by this. And well, what we did here was we had the galaxies, we measured them using like angular distance or some sort of redshift calculation, which gave us a specific distance, which I think was 43.2 megaparsecs away from Earth. And then if you use four-dimensional geometry, it gives you a total value for the radial distance of the hypersphere at 14.4 megaparsecs. But since this value is calculated all for sessional velocity distances, it's unlikely to be correct unless those distances just happen to be correct, which they may be. Okay, so the second one was the four-dimensional stereographic wireframe model. This doesn't work because it's these are latitude lines, and then there'd be longitude lines, and then there's co-latitude lines in the fourth dimension. So you can see this yellow ball inside here. That's another latitude line in the fourth dimension. And they just keep going on and on into like as far deep as the number of co-latitude lines that you set. So that's the reason why this didn't work, because it needs to be a hypersphere model, not this longitude latitude wireframe model. So that I'll have to come back to that. And the other thing was to get the recessional velocity distances, so that essentially the you know, the what's that thing called, the Hubble constant, and that gives you when you graph that, you get a line with a certain angle, which I think is like 70 or something. So like I said, it's been a while since I looked at this, so I'm a bit fuzzy on the details here. But basically what we do is we project the galaxies off the hypersphere, and then we tried to match it to the known redshift values based on the Hubble parameter. And what we got for that then was a radius of 4,320 megaparsecs for the hypersphere. So that sounded good, but once again, it's based off recessional velocity distance measures. So there's also some problems with calculations. I assume I'm referencing this kind of scratchy line down here, but this was the image I could find of the initial results. But it is, if you go back and look at our previous tags videos, you will be able to see these calculations performed live there, and you'll see the actual graph. But this is very close anyway. Okay, so the conclusions of all that is that the SVM model cannot be accurate because it is dependent on recessional velocity distance measurements. The APC distances, which is the anamorphic perspective cosmology distances, as a function of redshift, is unlikely to be accurate due to the likelihood of methodological errors, which I won't go into in detail, but I think we discussed them somewhere else. So, well, actually, the main point is that there's just a low chance of accuracy because recessional distance is more than likely flawed. Problem: more accuracy is required to calculate the redshift difference between transpiring from the hypersphere to tangent plane. So the current estimated accuracy was 1 to the 29, so 1 with 29 zeros after it, which exceeds Python accuracy by many orders. So the solution was to use Wolfram Mathematica, which is probably the next part. So APC distance measuring method so this is the high precision method using high precision values. So initially we just input, we have 2 pi or, where or is the radius. So that gives circumference of the hypersphere at 2 megaparsecs. So so the semi-circumference then is 1 megaparsec. So this was we just wanted to start with a kind of a low value to see what results we get. So we need the normalized value for that half the circumference. We divide the hydrogen wavelength by its value to get the normalized value, which is this very long number here. So we can see that's 10 to the minus 29, which is the kind of accuracy we need at this point. So this should be the displacement d of our other values, s, which are these, which divide the hypersphere into 5 evenly spaced interval longitudes. So those are these, and then we must take the sine and cos of these s values as follows, and they give us the coordinate values, and then the sine and cos of s plus the displacement gives us these values, which creates d1 and d2 respectively. And these results need to be calculated by the 1 minus c component derived by the cos calculation. This gives us the projection of d1 and d2 onto the tangent plane as P1 and P2 respectively. So P1 and P2. Right, the distance between each of these values needs to be the difference between, yeah, the same thing. So the difference or the distance, P2 minus P1 gives D3 for each of the reference coordinate values that we were using. So we see we get 10 to the minus 17, 10 to the minus 16, then it goes up again. So it's a bit strange. And then divided by the normalized wavelength of the hydrogen element to obtain the redshift values, or so these are the results. So we get 4, 1.6, 4.44. We get an error at this location, and then 10 to the minus 13 there. So yeah, so 10 to the minus 11, 10 to the minus 12, 10 to the minus 13. So these are essentially what's going on there is we're getting we're taking the hypersphere and we're putting lines on the hypersphere, and then we're adding a small amount, which is the amount of the hydrogen element in the rest frame kind of lab, you know, and then we project that out onto the tangent space, and then we measure the distance between each of the lines as they're projected outwards, and then we divide that by the we normalize that again using the, where it says it here, normalize using the wavelength of the hydrogen element again to obtain the redshift values. So that gives you the redshift values on the tangent plane as a function of distance out from the hypersphere. Right, so if 2 pi or, yeah, so now we're going to up it from 1 megaparsec for the half circumference to 6 megaparsecs. So we just go through the exact same process again, and the result is the exact same, 10 or 4.16, 10 to the 11, 4.44, 10 to the 12 error, and then this one again. So that's a bit strange. So what I noticed there was that basically, even though we have this greater accuracy, or we're working off a greater accuracy system, this implies that, well, we'll just keep going anyway. So we get 2,160 megaparsecs, and we get the exact same results again. So there's something wrong with that. So effectively, if you look at the conclusions, then we say Wolfram Mathematica failed to produce differentiable results using hyperspheres with half circumferences of 1 megaparsecs, 6 and 2,160 megaparsecs in length. The results provided suggest that all of the usable redshift values for each of these 3 spheres must be contained within 1/5 of the angular distance from the projection point, which is up here. So it's all kind of, basically all the galaxies have been compressed into this area up here, which is not what we'd expect. We expect it to be more evenly spread, and actually the denser ones to be further down here. So this seems asymmetric and unlikely. Unexpected results appear to emerge from much smaller, expected results appear to emerge from much smaller circumference distances on the order of 300,000 kilometers. So this is speculation. So we don't want big values for the hypersphere, it appears. We'd want to, in order to get all the galaxies away from the top and move them down here, we're going to have to shrink the radius of the hypersphere significantly. So it won't be in the megaparsec range. Therefore, Python accuracy is sufficient to calculate these problems. So we no longer need Wolfram Mathematica, and I don't have to pay for it, which is good news. Smaller radiuses for the hypersphere. Is the hypersphere really only hundreds of thousands of kilometers in diameter? Seems a bit small, doesn't it? Anyway, so here's the methodology just written out in kind of coded form. So we have the radius that we're looking for. This is the radius of the hypersphere. The norm is the radius divided by pi. Then we have the hydrogen wavelength element is this. And then the displacement will be h lambda divided by the norm. So then we get the intervals of the hypersphere. using n equals 1600. The thetas is this, then the coordinates, sine and cos of those. Then we get the displacement and the coordinates of those, and then stereo project all of that. Then we get the displaced intervals, which is we just minus one from the other here to calculate the redshifts, and then get the norm of all of that to get the, presumably, at some point you get that anyway. So you can calculate the distances by accumulating, oh, this is 4D and 3D. So yeah, I'd have to look over that, exactly why this step is needed. So yeah, but that might be, that's how we are producing the next set of slides, I guess, just graphing once we've calculated the distances. Okay, so here we have, using a radius of this value. So I believe this is the totals. This is the semi-circumference value in kilometers. So when we use this value, we see a small amount of deformation in the curve that we're getting. So along here, this is redshift, and up here, this is distance. So we're saying, if redshift equals 4, we get 10 million kilometers, something like that. Then we have, if we increase the value of the radius, we see that we're getting larger deformations in the curve. So that might not be good. And then if we go above a certain value, we get unexpected results. So this is model failure, error probably resulting from encountering the limit of Python precision. So that makes sense, because we did say there would be a cap on how big we can make it. So just kind of going by eye here, which is not, the done thing to do, but basically what I'm saying is that this curve appears to have like the least amount of distortion, meaning that, on the higher end of scale, meaning that the results are good and the model is not encountering any fluctuations or perturbations in any sense. So that would be with the radius of this value. So, and the diameter of this value. So hypersphere dimensions and statistics and specifications based off that value, which was like the smoothest curve. We have a radius of this size, a diameter of this, and the circumference is this. So the semi-circumference was that value at the top, and that gives us a surface area in 3 dimensions, I guess, of this and a volume of that. So quite large. So, but we could also apply maybe different constants and try and see if we could find a relationship between, the electromagnetic force and the gravitational force. So if we have a hypersphere with a semi-circumference of 501,000 kilometers, then the diameter is this value, which is close to a light second, or the distance that light travels in a second. The surface area divided by the gravitational constant g gives 1.2 10 to the 36 power. So that is close to the electromagnetic force divided by the gravitational, or for the photon-electron interaction. So the strength of these two forces for the photon-electron interaction. The volume of the hypersphere is 3.1 10 to the 33rd power, close to the difference between the weak and electrogravitational coupling constants. The volume of the hypersphere divided by the gravitational constant is this number, which so this is the volume here divided by gravitate g equals this number, which is the electric force between a proton and electron is around 10 to the 43 stronger than gravity. So they, it's close. It's not exact though. Pressure differential is 1.673 10 to the minus 18, which is close to the electron volt. So that was what I was looking at. If we go on, we have thin film galactic interference sort of research here, which is galactic polarization using Newton's rings. So again, sticking to our semi-circumference of 501,000 kilometers, we get the constructive and destructive interference fringes with a lambda of 400. So that's the wavelength. There's our diameter or radial value then, because we divided by 2 times pi. This is just a value that needs to go in. So for destructive interference, that's the equation, and the constructive interference has this equation, and we get these kind of patterns out. So this is the polarization pattern based on lenses from Newton's rings. So to begin with, if we want to actually do this, first we take the hypersphere with the galaxies on it, and we project it down onto a 2D plane, so we get this projection view. So we start with destructive interference. I mean, with a scale factor of 900, that was the basically we're scaling the so that everything fits together. So it's an extra value, if you like. All of the galaxies fit in, most of them, like up to a point, like the distribution drops off. They'll all fit into the yellow section when the scaling factor is about 900. If we set it to 3,333, we see that the yellow circle perfectly fits in one of the Great Walls, and another Great Wall out here fits on that line, and another Great Wall out here fits on that circle, and so on and so forth. If we go for a scale factor of 6,666, we see that one of the Great Walls sits around the green circle, and there's certain amount of alignment on the other circles as well. Basically, they get a little bit more dense before each new circle begins, and so then with a scale factor of 9,999, we get perfect alignment between the first Great Wall galaxies and the yellow interior line. Oh yeah, I also note that there's a denser region in here and around there. But this seems to be quite a good alignment as well. It's obviously a Great Wall of galaxies around this line, and then they begin to fade out, get a bit more dense, and so on and so forth. Not really sure if I should go into this. Is the Earth flat, spherical, or concaved? I don't know if this is really that relevant. It was interesting to me at the time, but I suppose, maybe there's a way I can make this make sense. I mean, if we're talking about a radius of, semi-circumference radius of, so this is in meters, obviously, up here, 501 million meters or whatever. If we talk about galaxies with a redshift of like 1, then that's 0.5 million kilometers away. That's much smaller than what you'd get with a normal, like using recessional velocities or whatever. Something with a redshift of 1 would be very, very far away. It would be like possibly in the hundreds of megaparsecs. So this is next door compared to that, if it's only 500,000 kilometers away. And that means that everything that exists in this space here is obviously much closer. So that would kind of suggest that a lot of the objects, in the Milky Way galaxy, for example, would be very, very much closer, and possibly even in our solar system. So things could be a lot smaller, they could be a lot closer. not saying that's correct. I was just, at the time when I got these results, I was like, okay, it looks like everything is much smaller and much closer to us than we initially conceived of. I don't think that's the case anymore, which is why I kind of held off giving this presentation, but I'm just giving it now because why not? So there was some, at the time I was making this, there was some final experiment where they went to Antarctica to prove that, you know, that there's a 24-hour sun in Antarctica, and there is. So, yeah, so there's all this stuff about differences of distances, and I think we can really kind of skip a lot of this stuff. Yeah, there's the idea that under the APC model, the Earth can either be round, flat, or inverted. That's only true if there's a total relativity among each observer in the universe. So there's a trade-off here. Basically, if you want a relativistic motion, where every person essentially has their own hypersphere, if you like. So, you know, if let's say we're at the bottom of the sphere here, and this is the projective point. As we move up, the projective point would move as well. So it would always look like you're at the center of the universe in terms of redshift. You know, everything would be more redshifted the further away it was. However, if this point up here is fixed and the Earth is at the center, then if you move up here, like halfway, all of the galaxies up here would be redshifted and all of the galaxies down here would be blue shifted. So it'd be quite obvious that the Earth was at the center. But if it's relative, then the Earth would be able to change shape. It would, and the Earth is like here, it would, I think you could get a situation where the Earth would turn completely flat once you were halfway up the sphere, and once you got to here, it would completely invert, like the sphere below. So that's it. That's your trade-off. Either relative motion with respect to the hyperspheres exist, or, and in which case you have to give up the shape of the Earth being that, you know, that becomes completely relativistic depending on where you are in the universe. You know, or so if you have that, then it is preserves the idea of us not being at the center of the universe. But if you decide, well, I'd quite like the Earth to be a spherical object all the time, then you have to give up the idea of like this sort of maybe relativistic is the wrong word, but basically the Earth has to be at the center of the universe in that case, or at least the galaxy. So linear regression machine models. So we have our, you know, we have our curves for our galaxies based on distance and redshift, and we want to generalize that so that when we put any galaxy in there, we want to know exactly how far that is based on its redshift. So, you know, to start with, I just used a simple linear fit with the linear regression model, and it gave a slope of, well, this could be some early results. I might want to redo this. So the slopes aren't really that important here because I used a number of different versions of this calculation. But you can see it's a straightforward line. So it's gives you an idea of the different sizes, but it's obviously not going to be, it doesn't really conform to this curve. So I tried to use a more logarithmic fit. That didn't work either. It's almost inverse to what we'd expect, so that wasn't good enough. I tried neural networks as well because they handle nonlinear functions, which is what we're looking at. But amazingly, they weren't able to do it either. So yeah, so they were the results. You can see the accuracy is basically 0, or it's very small anyway. So there is another way to do this, going back to linear regression. If each, you see this curve here is a nonlinear curve, and this would be distance in terms of redshift y. So distance on the z, y is the redshift. But if we go this way, we see that this line is linear. So we can So essentially what that means is if we chop it up horizontally along this y-axis, we will get a lot of linear functions, and that can be shown here. Here's an example of some of those linear functions, which are the distances, which correspond only to the distance measure. And then we can use that then to create a number, like a great number of linear regression models, and then project each of those out. And then when we take the cross section of those, we will get our the distances in terms of kilometers, or as a function of the redshift. So this is with a hypersphere with a radius of 14.4 megaparsecs, and we see that it goes up to 7 times 10 to the 23, and that's going up to 3 million redshift. So that is huge, because at the moment we've only ever seen up to like 13. I think they went up to 16, and that basically doubled the age of the universe when they did that. So you can imagine what going up to 3 million would do to the age of the universe. Obviously that model is wrong. Hypersphere radius with 2,160 megaparsecs. Yes, so here you can see that the size is. Hang on a sec. So here we can see the size is going up when we double from 2160 megaparsecs to 4,320 megaparsecs. Goes up by nearly a factor of 2. You'll notice that the redshift values don't change though, and that's because they're being left out of our out of consideration when we're using the linear regression models, and that was just done because it was initially an oversight, and I just decided to use a reference set of redshifts to cover everything just for expedience sake. But in fact, if you transpose the original model in a different way and take cross sections of that, we see that the redshifts aren't linear. It's going up in a zigzag motion, and so we can see that it starts off at one kind of area and then it expands. And so at a certain point, these lines, the way they're starting, they're going to hit 0, and in fact they're going to go below 0. So we will have negative redshift values, which are essentially blue shift values. And that is interesting. So does that mean that when this line hits 0, which is around here, so it would actually be this line that we want, does it mean that when they start going to 0, that that's essentially equivalent to our model breaking down, like in it's further back than I thought, like in this instance, or when all of the galaxies get bunched up here? That's the kind of thing we'd be moving towards, like basically an unrealistic model of the universe in some sense. And then presumably a lot of the values down here would be unrealistic as well. So that's something to do in future, to combine this data with this data to create an actual plot that makes sense using kilometers and an accurate redshift down here, as opposed to just the reference one. But it will still be quite a large redshift, I imagine. So decision tree results, distant calculation machines. So the best fit that we can get for a nonlinear function is using a decision tree. Presumably this is the radius of the hypersphere here. We have a decision tree with a maximum depth of 89,226, which was a function of the amount of galaxies that we have in our data set as they are projected onto the 0th line of the what's that called? Right ascension data. But anyway, the decision tree regression takes averages of ranges so it distills ranges into a single number. This heavily quantizes the data, as we'll see next. So here's all of the galaxies then plotted out of the decision tree model. And you can see that what we mean by heavily quantized, all of the galaxies now are no longer spread out, they're confined to these ranges. So we can overlay the APCs with the recessional velocity distance. We see here's our galaxy at the center. The red dots are the recessional distance. I'm not sure if this is entirely accurate or if this has been scaled by a factor of 1,000, but either way, it's roughly the same. You see they're kind of spread out, and what we noticed from the APC calculations is the galaxies are a lot closer. But this is based on a very small hypersphere, and we still haven't settled on the exact size of the hypersphere yet. We will once the previous work is finished, though. And this is with Z redshift, so you can see that here they are overlapping much more. So this is just, you know, the Z redshift. So this is just for comparison's sake. It's not, we're not building any conclusions off that. So if we look at the quantized redshift values for the galaxies and their distances, I would ask you the question, what does this remind you of? And the answer, I'm just going to tell you, is it looks a bit like compact disk encoding to me. So the idea is we can take our galactic data and unwind it to get something resembling this magnified view. So this is the CD, and these are the sort of the digital data that is represented by some sort of pulse code modulation. So the idea here is to create like a kind of galactic Rosetta Stone, where we could like read information off this disk if we like. So here's the disk, then we polar transform it to get, and the reason why I called it the Rosetta Stone is because this scribbling kind of reminded me of what was written on the Rosetta Stone. Unfortunately, I wasn't able to get much further than this. You know, obviously this would be some sort of binary data in this sense, you know, and then but it's hard to extract this from this image and turn it into actual binary data. It is possible, but it will require more work. But if anybody wants to attempt it from this image, they can. But I would argue that it's not the way to go. Obviously, it's too painstaking and possibly impossible. So in conclusion, large values for the hypersphere radius produce unsatisfactory results, or so it appears. Yeah, no, actually, I would say that that is correct. Hyperspheres with small radius values violate current cosmological models. Well, that goes without saying. However, they appear to give good results for physical coupling constants and thin film measurements. That could be debatable because they weren't that accurate, we noticed. And the thin film measurements is just sort of an aside, and you could probably find concordances with any hypersphere size. So we don't put too much stock into that. Linear regression and you know, artificial neural networks ran into limitations. Decision trees provide usable normalized results for use in anamorphic perspective cosmology and recessional velocity comparisons. Redshift is an unsatisfactory measure for use in determining hypersphere radius sizes. So what is the correct feature to use? So the possible solutions would be quasar space-time curvature, angular diameters, and spectral radiance of the cosmic microwave background radiation. These are just other possible metrics that could be used instead of redshift, although we might argue that maybe redshift is not a totally unsatisfactory measure based on some of the results in this slideshow. So we're going to look at that. I've looked into quasar space-time curvature. There's not enough data on that, so we can't use that. angular diameters of the galaxies are also, they would run into the same problems as the redshift, so they're not usable. As for the spectral radiance CMBR, I did a quick analysis of that, and I found that with a hypersphere of semi-circumference of this value, the temperature of space would need to be very small in order to get a kind of black body spectrum radiation curve that we might expect. And if we looked at, you know, if we put in the value that we normally expect from a lambda CDM model, then we get, or just from, you know, well, even we'll just stick with that. It doesn't, you know, it doesn't give the correct kind of curvature. Obviously, the curvature is in there, but it's at such a small scale that it's not actually, it's not comparable. And then the spectral energy CMBR using the same values obviously goes off the charts. So using the lambda CDM kind of Kelvin temperature for space. So there's just the equations then for the spectral energy, Planck's law, and spectral radiance, which I guess involve things like Boltzmann constant and temperature, Planck's constant, and so forth. Okay, so we see it goes off the scale, so that's not going to be used either. So probably just stick to redshift values, and I could have the results by summer. That's the end of the slideshow. Thank you. I don't know if that was.
Yeah, thank you.
Thank you.
As a new results you have, are you still working on that, or is it the?
Yeah, as I mentioned, like I started that about. I was working on that about 2 months ago while I was sick over the Christmas, and I was getting all these crazy results. You know, it seemed like everything was much smaller than it appeared. But then I kept refining it, realized that I was wrong, and then that's why I was saying, well, maybe I need to look into angular distance and you know, spectral radiance and stuff like that. But in the end, I think that we can possibly get a good enough model just using the redshift distances. Because, you know, remember that spiky graph I showed you? When that starts to, if that goes below the 0 line, we could say that's a negative result. So we could just use that line where it's like nicely close to 0 and say, this is our best guess. And then use that data to see if there's any interesting concordances with, as I said, with the physical constants and the thin film, you know, Newton's rings. And if there is, well and good. But if not, I'm going to call time on that research anyway. I don't think I'm. But maybe I should deliver that at the. I don't know. That might be good for the press conference if I can get that.
And how many observational station data used? One or more?
Yeah, for the galaxies, it's all taken from all the data is taken from the SDSS, which is a Sloan Digital Sky Survey, which is comprised of 2 telescopes, which are really
only good. Is not good. If you use only, it's not good. You don't get correct data.
We got two telescopes.
Okay. It's
one is on the north. Yeah, one is on the south.
And how distance was between 2 observation telescopes?
Sorry, what? The distance?
What distance between 2 telescopes?
Yeah, one is on the northern hemisphere of the Earth, and the other one is on the southern hemisphere of the Earth.
It's correct.
Yeah, so they're very distant from each other. Was there anything else about that? So they're basically big digital cameras, and they scan the sky and they take photographs the whole way along, and they're very there's a lot very technical.
And you didn't get the data outside from Earth, from telescope which is outside.
No, it's all taken from the Earth. It's amazing what they're doing. Yeah,
because your data can be affected by the
atmosphere, disturbances in the atmosphere.
Okay, I will send. I can explain very well, but I will send you what I mean. Okay.
Yeah, well, they'd be disturbed visually by like disturbances in the atmosphere, but be aware this is not my data. This is data from like the Sloan Digital Sky Survey. So they're very professional astronomers, and like anything like that they would correct for. If there's something else that they don't know about, then they won't be able to correct for that. But yeah, so that's it.
And another idea perhaps is something I don't know is good or not. Yeah. Why you don't try to go into the quantum direction? You can go exactly what you go in a macroscopic field. You can go inside into the quantum direction, and try this thought in such a way.
Well, so the work I presented there was cosmological work.
But perhaps I am wrong. But if you go inside in a microcosmos, you can easier get. You can see all is behind of you, but outside is harder to you look outside, like in case of inside. In minimum space, you can easier to imagine. Well, but if outside is more harder.
Well, Laszlo, I'll just go back to this. Let me see if I can share the screen again. So you make a good point there, Laszlo. Thanks for that. You kind of reminded me of something as well. If we look at this, no, sorry, not that. This. So this is the hypersphere, yeah, in 3 dimensions. So we're losing 1 dimension just so we can look at it easy. All the galaxies are the black dots that we see, and the Milky Way galaxy be there at the South Pole, and then these are like very distant galaxies, and very, very distant, and then we get up to the projection point on the North Pole, which is the antipode to the on the hypersphere. The term pode and antipode are usually used for in cosmology to denote the I think it's the observable universe, which is constantly expanding as at the speed of light. But we are not using that methodology. In our methodology, the entire universe is contained on the tangent plane, which is this flat plane that the sphere sits on because it's being projected onto that. That's neither here nor there at the minute. The point I want to make is that as we go up the side of the hypersphere, distances are going to get smaller, and presumably time also dilates. So once you get to the point at the projective point, time is going to stop completely, and distances will contract to nothing. But along the way there, you're going to find that certain like if there's galaxies all the way out here, which we'll assume they are, those galaxies are going to get smaller and smaller, and they're eventually going to cross a point where they will, on the hypersphere at least from that perspective, cross over into the quantum realm. And that was the whole point with this research, which was a total failure, but would have been fantastic. So the idea here was that this is a little bit hard for me to explain because, like I said, it's been a while since I looked at this, but the basic idea is you can imagine if this 0 point here is the projective point at the North Pole, and then further out here, maybe, you know, way further out, is where we are. So as we move along this line, we're moving up the side of the sphere, and the point is that the energy would kind of increase to infinity. So it's a bit like Planck's energy, you know, that problem with the ultraviolet catastrophe. But yeah, so it was a Planck's equation then, or formula or whatever, solves that by taking discrete values. So you know, it no longer goes to infinity, but there's some sort of peak here. And I was thinking that we could project that kind of curve then onto the sphere, so that at a certain point, the galaxies will get so small that they cross over this sort of quantum threshold, if you like, and they become like quantum particles. So if you had and they would act like quantum particles in some sense as well. So that's at least the insinuation, or the, you know, one interpretation of that. So if you have a powerful enough telescope that you could see out beyond that point of that inflection point, galaxies would be like the galaxies that we're seeing now are already beginning to behave strangely, unexpectedly, from the point of view of cosmologists and their current theories. But I suspect that the further we look out, the more intensely strange these galaxies are going to be as quantum effects become overlapped with the cosmological effects. So in a sense, I think that kind of answers your question, that yes, indeed, this model is not only about the big, but about the small. And actually, if we go further than that, and this is where it gets interesting and a bit weird, if we imagine that there's all of these galaxies up here, which are actually atomic particles, and that's going to a point at infinity. So there's like an infinite number of these particles at this point, and they're being projected straight down onto the tangent plane, or onto where the hypersphere touches the tangent plane. And that means, in some strange way, all of the atoms that exist on the Earth are actually galaxies that are infinitely far, well, not infinitely far away, but that are infinitely kind of small and being projected from a distance, which, from the perspective of the tangent space, is infinitely far away, and also exists in every direction you could possibly point in. But when we talk about 4 dimensions, it is a finite distance away, and could potentially contain all of the information that is needed to generate everything on Earth. And those things technically are galaxies that are like really far away, or really small and really contracted. So essentially, this is not just a theory of the universe and distances and of galaxies and redshifts, but it also seems to contain what we are. You know, this kind of concept of that we find on the Emerald Tablet of Thoth, I believe it is, as above, so below. Well, that's exactly what we've got here. We're saying that the galaxies, when we look out into space and see the galaxies, and then we ask, well, what are we made of? We are made of those galaxies, like the furthest ones away, the ones that are even outside of space and time. So so it's a closed loop then. If you get to the biggest space in the universe, you wind up at the smallest space you know, like touching the table that or your laptop. They're all, it's like, again, it's like a loop, which is interesting because I think, who's that physicist, Leonard Susskind, he spoke about that. He's big into this pode, antipode, visible universe expanding, which I totally dismiss. I think it's not a good way to model your universe, but it is interesting in the sense that they think of that as like a black hole, in some sense, and then they have a lot of other kind of mechanisms that they use on that. So, I mean, there's something to be said for that in the sense that you could think of the projective point as a bit like a black hole. It's there's no space there. Time is completely stopped. It's a singularity. It exists outside the universe, and it would be infinitely dense in the sense that there's an infinite number of particles or galaxies contained within it. But the whole point, I think, that Susskind was making, and the other people who work on this kind of, is it some sort of entropy model of the universe where so basically they're saying that when you get to the really big, you will get to the really small, and vice versa. That it's kind of like a Mobius strip or something, or like a circle. I think that is kind of informed by some sort of Far Eastern, maybe Taoist philosophies about the large and the small. I'm not entirely sure, but what we see here is that it appears in this as well, and in not just a hand wavy kind of, well, they must be connected in some way, we just don't know how. It's like very explicit in the model that this has to be the case. So that's another reason why this is a good model, I think.
Okay.
Thank you.
Thank you.
Yeah. My this thing showed. I think one of the papers, recent one, signals. I saw the limits when the temperature is absolute zero, when the temperature approaches infinity. I think we discussed that. It becomes like a vacuum 0 point. So essentially, you are saying that it is like a micro black hole type of thing. So I think if it's a quantum regime, we should be able to have both wave and then particle, which means that CMBR as well as gravitational waves, we should be able to use them, and then figure out, the differences. So if it is in the same spot, you measure the CMBR that's coming there, and also the gravitation wave. If we compare, if you use these two values together simultaneously, you should be able to figure out, able to prove.
Well, that's the thing though, Rajan, because you saw the graphs for the CMBR, and they produced the results. Excuse me, the results were not good. I couldn't get anything out of them. So either I need to go back and study that more to see if I can get something out of it. But it was a bit depressing to see that. But it wasn't, it wasn't too bad, because I mean, there's a lot to think about on that front. Like if I'm saying, oh, you go up the side of the hypersphere, and then you reach this critical point, a turnover point, where like things like go beyond the Planck limit or close or into the atomic realm, or like even or the quantum realm, let's say. So I assume that's like that must be some distance. Like there must be some limit distance that we're talking about. And I don't know what that is. That like 10 to the minus 16 or something? Or that might be the classical radius of the electron. So if we find that point on the hypersphere, the equivalent point that, okay, galaxies are going to start becoming quantum at this point or something, then we can plot that on the hypersphere. But I don't think that is the same. You see, I think there was a gap in my understanding. When you see that curve for the black body spectrum, the peak does not represent that turnover point that I'm thinking about. It doesn't represent it just happens to be another peak. Like because the I think it's the x-axis is the wavelengths. So those are all valid wavelengths, and they're all quantum wavelengths. So there is that graph is not describing any shift over into from macro to quantum, which is what I thought based on my understanding of the ultraviolet catastrophe and this sort of exponential curve. I thought the discrete kind of quantum values only kicked in to get rid of the exponential curve, but they don't. They're actually throughout the entire continuous spectrum. So that's interesting. That was a misunderstanding that I initially had. But then so it's dead in the water at that point. We don't need to discuss it. But if we imagine that we were projecting that black body spectrum onto the sphere, then projecting it back off onto the tangent space would mean that it would be at near infinity. So it would be almost, we would not be able to extract any data out of it. That's a problem. But also, if we flipped it so that the spectrum is closer to the universe, it will just look like the spectrum that we have. So we don't have any, we can't get any new data out of that. And then also we have to think that spectrum is everywhere in the universe anyway. No matter where we go in the universe, we would always get the same values. So it's ubiquitous. It isn't related to one part of space or the other. So from that perspective, we can't map it to the hypersphere or the tangent space, either podally or antipodally. It's just everywhere. So that is another sort of correction to the theory, if you like, that I'd like to point out. Now, as far as what you're talking about, the relationship between CMBR and gravity waves, I don't know what that relationship is. I don't know, why would you even think about connecting those two?
No, I'm saying that the particle side or the matter side, you have any type of interaction like binary interactions will produce the gravitational waves. So
and we can see from our side too.
Yes. So that's the independent data we can get. But I'm saying that if it's a quantum thing, it should have this both particle side and also the wave side. And the wave side is the CMPR. But you can also look at the particle side. If they are interacting, we should have a gravitational wave. So I think main thing is the discontinuum. I think the Emery that I'm working with, I think the discontinuum physics may answer this question.
I don't know about that. Yeah, I think the work you're doing with Emery on discontinuum physics, it's pretty interesting, and it sounds good. I would keep that going. I'm not entirely sure what you meant there. Sorry, Rajan, you were talking about, so you have the particles, the waves, and so maybe the particles are connected to the CMBR, were you saying? And the waves?
No. Particle interaction, gravitational waves. If they are really having a high-level interaction, it should produce gravitational waves.
Oh, okay. So maybe then what you're saying, like if I'm trying to understand this or apply it to my work, you might have like at the projective point of the hypersphere, there'd be a lot of particles there interacting. Yeah. So would that generate gravity waves? I don't know, because the weird thing about the projective point is that mathematically speaking, that point is not in the set. It actually exists outside of the universe. So it should not be able to directly interact.
They're not real? They're not real particles then?
No, they are real. I mean, the projective point is real. In fact, it's probably the only real thing in the universe, because if the projective point cannot see you, then you do not exist. It is like the all-seeing eye of God. If its light does not shine on you, then you do not exist. Okay.
Or it could be a dark matter then?
No. Well, no, it's nothing to do with dark matter. In fact, dark matter. Oh well, dark energy is totally ruled out of this model. Dark matter is allowed, but it's different. Dark matter is a type of space. It's yeah. There's three types of space. Ordinary space, and sorry, I'd have to look that up again, but there's, this Gibbs mechanism where you put a drop of it's like a solution a particular chemical, like
Surfactant?
a surfactant. Thank you. So then there's surfactant space. Yeah, and then you can have a third type of space, which is kind of oh, you know, surfactant space is the one that is that does not exist in our universe, and if it did, that would be the end of the universe. So when that is, if that was introduced, it would just wipe everything out. But the other one, which is the dark matter space or just dark space, that, you know, could it's basically just a different kind of space with a different gravitational constant, and it explains. It solves the problems that are occurring between dark matter and MOND, those two competing ideas, because I think there's MOND came along, which was the modified gravity, you know, that's fine. But then you have these clusters that come together and then they go through each other and they left some of the dark matter behind them as a residue. And that shouldn't occur in a MOND universe. So that kind of ruled out MOND, but then there's other things that rule out dark matter in favor of MOND. So that's why I'm thinking there must be a third solution. And that third solution is to say, okay, it's not dark matter, but a new kind of space, which is another kind of liquid that doesn't mix with ordinary liquid space that we're in, if you like. And that does make sense then, because if there's this liquid, then it would have some sort of a surface tension, and that would stick.
Is it superfluid? Is it superfluid?
That I don't know. This is where you and Wenzong need to come in. You need to get on board with my work and start, you know.
Yeah.
You know.
Okay, recently I saw.
Start putting in your expertise in there, and I mean, I know you have other things like discontinuum physics, and that's great. And also, I think Wenzong has his own theory on tired light.
Yeah.
So you know, when you've got your own pet theory and you're wedded to it, I understand that there'd be problems just adopting a new theory. But there's another way to work, which is to say, well, maybe you don't believe what I'm saying, but you're happy enough to contribute. You know, that kind of way. Like, for instance, imagine if you had like a project lead, like you were hired to do some research into a subject, but it's not your like pet project, but you kind of just lend your technical skills and time to it anyway, and see what comes out of it. I don't think there doesn't seem to be enough of that in our community. Everyone seems to like, I have my theory and I'm not moving away from that kind of theory. But like at the same time, there's also issues like how do you apply like your knowledge to, if someone like, let's say Christian or something, he's got very you know, you would
high space.
Yeah, it would be difficult to, okay, well, you know, I'm happy enough to contribute to that as much as I can. You know, I've done my best to contribute to it in certain kind of small ways, and also trying to, you know, also you can also contribute to something just by criticizing it and saying, well, there's a problem here, you know, and I think that's important. But people need to be open to the criticisms before, because that can really improve a theory. For instance, I was working on my thesis, and I finally got some feedback from one of my supervisors on it, and completely changed the course of my thesis. And I realized, oh, like, you know, all of my results are wrong, and I was able to go and correct them. But so without that feedback, and he didn't even really give criticism. He just gave one pointer, and it completely shifted the entire project. So that's important, to listen to other people and to take their criticisms on board. And, you know, I mean, obviously there is ways to criticize what I'm saying, but I think it would be better to just prove it or disprove it. I don't think you can disprove it experimentally at this stage, but there might be a way to do it.
Not falsification.
Yeah, no, I suppose it doesn't need to be falsified, but, you know, like, for instance, the concept where I was attempting to explain the overlap between the quantum and the macro and how we are, like, is it correct that all of the galaxies, like that there's an infinite number of galaxies at the projection point? And I don't think that's true, because that would mean that it is a black hole, because you have like a density thing. So it wouldn't be infinite, but the amount there and in the vicinity would be equal to the number of atoms or particles on the Earth, let's say, or maybe in the Milky Way, you know. So that to me seems reasonable. Yeah. Because as we notice, there's an awful lot of galaxies at the bottom of the hypersphere. But as we go out, up, you know, they become less dense. So there will never be a full singularity, like a density singularity. That won't take place. But there are singularities on the hypersphere, I believe, and those are the quasars, which stretch further up to the projective point, and then when they're cast back down, they have higher redshift values, which is why quasars, which are, as Holt and Arp showed, are connected to certain galaxies which are relatively nearby, have the appearance of being redshifted to an extreme. So they're not actually. It's just the fact that they're closer to the projective point than they appear. You know, but
illusion. Yeah. It's an illusion.
Yeah. So it's similar to like if I have this object, I have a light source here. And the object will cast a shadow on the wall that's larger if it's closer to the light source. The further away, the object and its shadow will become more into line until they line up perfectly, and that would be so that's the case. And because we're dealing with it's a strange thing though, because the light source we're talking about is a point light source. It is it has no extent, and that means that whatever is being projected will not be blurred. So if you have a point light source, you have perfect edges, so you won't see a blur necessarily. But so I'm not sure about because that's the weird thing. In some ways, the redshift that we are seeing is the result of an anamorphic perspective lengthening of the object as it's projected onto the tangent space. But is that a blur? No, not really, because again, everything that's projected is projected with 100% fidelity. And that would be true of these quasars as well. So,
are there a Doppler effect? Anything like a Doppler type effect?
Not really, no, because you see, there's no motion. Nothing is actually moving. Because that's the whole point of the recessional velocity distance with Z redshift, is that everything is moving away from us. And that's why it looks redshifted. But in actuality, in this model, we have the hypersphere and the tangent plane, and everything is static. There's nothing's really expanding. It's just being projected. Does that make sense?
Yeah. See, recently, Sabine had showed. Let me. Maybe I can just briefly.
Yeah, briefly, because we're probably gonna.
Yeah,
we said we'd keep the live streams to like 1.5 hours, but or 1 hour 40 minutes, something like that. So, but I did see there's a big, how do you say, like a big hullabaloo about some letter that you read online about particle physicists. Did you see that?
Huh? Which one?
Did you see? You're talking about Sabine Hossenfelder.
Yeah.
In a recent video she made, she read a letter. Oh no, so this is not the letter. Have you watched that video?
No, what is it called? A letter about what?
She read a letter. It was written to her anonymously or something. Or maybe no, she kept it anonymous, but it's about some particle physicist who's saying that the model that he's using to do his work is made up bull crap, you know? Like bullshit. Yeah. And then
there is one recent one. she was describing. There are two things. Like a few weeks ago, I'm trying to see that.
Well, what one are you thinking of then? Just give us the topic quickly, and I can look it up.
One of them is one of them is called the theory of everything. She was trying to.
Oh.
Somebody was saying, and that she sees that it could be true, but she doesn't. You have to look into that. But the main thing is that everything comes up random action. So the random action, they're shown that if you change the constants, right? If you say the constants are the same, initially you change the constants like gravitation constant and Planck everything. The constant is different. Then you get a situation where the conservation of energy doesn't hold.
Oh.
So initially probably the universe was like that, but then with the random fluctuation, it started to become constant. So that way, everything, you get all of them constant. So the conservation of energy holds good. So that's how we create the universe, something like that. So she says that was, that's something you can look into. But there was another one when she said it's totally wrong. Totally wrong. And that was what I'm trying to.
Okay, well, if you could send me on those links, maybe.
Yeah, I'll try to pull up that's like a few weeks ago. One of them is like a week ago. The other one was like a few weeks ago.
You know what? I can just look for that myself then. That's no problem.
Yeah.
I see that Laszlo sent a message. He said he's having problems with the... So I think he's gone. But anyway, we should leave it there, Rajan, because we're going into 2 hours and I have to do other things.
Yeah, like 3-4 hours, close to 4 hours. Okay. So... Okay, we'll see you, and then you can look into the things that I sent for your website, and then we'll try to contact Christian